Now let's consider some examples. Before that, let's introduce some notation that will be used throughout. So when I write bracket n, then that's a set consisting of all the integers between 1 and n. And if I write a, p, then that's a set of all integer between a and b. Sometimes I write 0, 1, which is all real number between 0 and 1, which is an interval, or for other number. But the context will make it clear whether we are talking about all the real number or just the integer. And sometimes when we have two functions, f and g, say n, we say that the f is big O of g, or if there exists a constant c such that f of n is at most c times gn for all n. So this constant c may be depending on other variable. If we fix say kt, there are some other variable kt. Let's say we always fix something and then we say this happens. Then if this c depending on k, c might be a fixed constant when k and t are fixed. So it could be a function of k and t, but if they are fixed, then it is a constant. So for example, if we say that fn is n and gn is say kn, and this is tn for fixed k and t, then we know that fn is at most constant this times gn, and once these are fixed, this is just a constant, so we write that the fn is big O of gn. And we say that gn is big omega of fn if there exists some constant c, say small c, such that gn is at least small c times fn. So these two are actually equivalent because this is same as 1 over c fn is smaller than or equal to gn. So this and small c are both constant. So these two cases are equivalent. So sometimes we don't want to actually find out the exact value of this constant c. Then, this is useful. So for example, in this previous example, so in lots of time, this constant is not so important. When k is large, this is not the major term. Even in this case, the upper bound we know is very large, much larger than the lower bound here, so that this is little of our concern. So we might as well just write that this is omega of k times 2 to the k over 2. Then this carries, all the essential information except some not so important ones are omitted. but if the notation becomes much simpler, so we write this way. And also we write Fn is literal of Gn if the following holds for any epsilon positive. There exists n0 such that for all n bigger than n0, we have Fn is smaller than or equal to epsilon times Gn. It means that if we consider these functions and if we let n grows, then Gn is growing much faster than Fn. So for example, Fn is n, Gn is n squared over 1 million. Then we know that for any epsilon positive, for all n bigger than 1 over epsilon to the, say 1 million over epsilon, what do we have? N is smaller than or equal to epsilon times n squared over 1, this, because n is bigger than this number, meaning that, this is actually, that's right, this is actually bigger than n. So this is Fn, and this is epsilon Gn. So in this case, this is literal of this Gn. And we again write the Gn is small omega of Fn if, so equivalently this, if Gn is growing much faster. So formally, for any m positive, large M, there exists n0 such that for all n bigger than n0, we have that Gn is bigger than m times Fn. Again, this is same as saying Fn is little of Gn. So that's some notation that we will use. And let's consider the concept of, let's consider some graph theory problem again. In graph theory, we say a tournament is an orientation of complete graph. So we consider directed graph when the H has a orientation. So an H could be oriented in this way or this way. There is direction on the edges. And you consider the complete graph and then you orient the edges, then you say this is a tournament. Why it is called a tournament? So you can consider two players, I and J, of some game, and you orient the edges in this way. If I and J plays together a game, and then I wins. If I beats F, then we write it this way, and the other way, if J win, then this is represents the game result of game result when all the players play each other. So which is what's called tournament. That's where the name comes from. And we write that the tournament T is consists of the vertices and edges. And H is that, let's say x comma y, or we just write xy is in E. or yx y comma s in E, but not both in this tournament case. And if xy is in the tournament, then we say that y is an out neighbor of x and x is an in neighbor of y. So that's what we have learned in undergraduate graph theory. And we say that a tournament T has the property Sk if for every S which is a subset of vertices with size k. So when we write some set and number, then that's consists of all the subsets of V with a size k. So this is our notation. For all sets of size k, there is a vertex V which has all vertices in S as its out neighbors. So in other words, in this tournament, if you have some set of players, then there exists one player which beats all of them. Then we say this tournament has a property Sk. So if this holds for all set of k players. So in general, if a tournament has this Sk property, that roughly means that there is no good way of ordering all the players so that depending on how good they are. So what it says is that you choose, say, k best player. So you choose k player, but there is another player which is not chosen, has beaten all k of them. So you might say that this player is better than all of this chosen one. So it is difficult to actually choose the best player, k best player. So one natural question is that for given k, does there always exist a tournament with a property Sk? That means, is there some tournament which it's difficult to pick the k best player, or it's not the case that for all tournament you can always choose certain, k best player in certain way that makes sense. So that was the question, and it's answered that for any k you can always find the tournament which has a property Sk, and it was first proven by probabilistic method. Say that if this inequality holds for n and k, then there is a tournament on n vertices that has the property Sk. So how do we do it? We again, let's say V is n vertices, which is numbers between 1 and n. Now what you do is we choose I and j, and we have to decide whether we orient the edges between I and K in one way or the other. We do this in a random way, random uniform way. We choose one with probability half, we choose the other with probability half, independently at random. So what happens here does not affect what happens here. Then this actually, provides a probability space out of, there are 2 to the k choose 2 different tournaments, not k choose 2, n choose 2, and each of them has a probability of being picked exactly, 2 to the negative n choose 2. And out of them, you choose one uniformly at random. So that's the same. So we consider a random tournament on the set B chosen uniformly at random. Let's try it this way. We consider a tournament on the set B, on the vertex set B, chosen uniformly at random. So, consider a subset K, which consists of K vertices. We let AK be the event that the bad event for having the property Fk. So event that prevents the tournament from having the property Fk is that there is no vertex that has all vertices in K as its out neighbors. So you have K, and then there are n minus K vertices outside. And if one of them beats all K, then AK doesn't happen. So for AK to happen, this doesn't happen, and this event also doesn't happen, and so on. So for every fixed vertex B outside of this K, we can compute the probability that B does not, let's just write beat all of K is 1 minus 2 to the negative K. So the probability that this happens is that for each K of the choices, you have to choose this specific way. And as they are independent, you just multiply together. So that's 2 to the negative K. And all rest of the case is exactly the probability that B does not beat all of them. And how many such events we have to consider? And all n minus K such events for distinct vertices are independent. So for this, and for the other event, so this B and this U, the event that B does not beat all of this depending on what happens here, and the event that U does not beat all of K happens, depends on what happens on these edges, and those edges are disjoint, so they are independent. So what do we have? Hence, the probability of AK is that V does not beat all of them, and U does not beat all of them, W does not beat all of them, and we multiply those probability, and this is the probability of AK. Then what's the probability that at least one of the bad events happen? There is at least one set of size K which is not beaten by a single one. Again, by using the union bound. This is at most n choose k times 1 minus 2 to the negative k times n minus k, which is smaller than 1 by our assumption. So that means, therefore, with positive probability, no events AK occurs. This means there is a tournament on n vertices with the property as K. And now, all we have to show is that for fixed K, there exists n which makes sure this holds. And actually, if you just let n be 1 plus, say, 1 plus root of 1 times k squared 2 to the k log k, then the above inequality holds. So here we write 1 plus root of 1 means that if you write, say, k squared 2 to the k log 2 plus some other expression. So we have a complicated expression, say, assume we have, say, 100 times k times 2 to the k plus 97 times 0.7 to the k plus 1000 times log k times k to the 100, or so on. If you want to optimize this, then you can write this. But all the later term, for large K, all the later terms are all smaller than epsilon times the leading term. So this is smaller than epsilon times k squared times 2k log 2. For given positive epsilon, you can always make sure that if k is large enough, this is small. So we can actually ignore this. We can just all write this as a term which is smaller than, strictly smaller than, this leading term. Then this is again same with this. So this is some function which goes to 0 as k goes to infinity. So this is smaller, this is a term which is smaller than arbitrary epsilon as k grows large. So on the previous, example, so these were the function of n, but depending on the context, the parameter that we are concerned depends on the context. So here the main parameter is k. So this is some term which goes to 0 as, and as k goes to infinity. And if you say that the fk be the minimum number of vertices of a tournament with the property as k, then above shows that the fk is smaller than equal to 1 plus little of 1 k squared 2k ln 2. And it's also known that this is big omega of k times 2k. It is proved by Socrates. So C here, if we say want to estimate certain function, and if we know just the magnitude, say, if you write it this way, then we just know that there is some large constant, say 1 million times this number is an upper bound. But if we write 1 plus little of 1, then that provides a more accurate upper bound, saying that this which actually determines the asymptotically what the constant that needs to be multiplied is. So let's consider one more example. And in order to consider the example, let's recall what hypergraph is. A hypergraph is a generalization of graph. It's a pair which consists of vertices and edges again. These edges may be called hyperedges, or sometimes just edges, where this B is a finite set whose elements are called vertices. And E is a family of subsets of V. And we say that a hypergraph is K-uniform if each edge contains exactly K vertices. And we say that the K-uniform hypergraph is called K-graph. So if we say K-graph, then it means K-uniform hypergraph. It's a generalization of graph because two uniform hypergraph is exactly graph. So more of a simple graph. So this is a generalization of graph. Sometimes it's called the set system because it's essentially the collection of sets. And there are, lots of studies going on this hypergraph alongside with graph theory. And one of them is about the intersecting hypergraph. A hypergraph is called intersecting if we have two edges, then they are always have a non-empty intersection. Then one of the natural questions is that what's the maximum number of edges in an n-vertex intersecting K-graph? What's the maximum number of edges in an when we fix the number of vertices and this has this intersecting property and it is a K-uniform hypergraph. In other words, we consider, let's say K is 3. So we consider this hypergraph. So there are two edges which are disjoint. Let's say this is 2 to the 2 times k, k, k. So this bracket k denotes that we are considering k uniform hypergraph, and this considers the number of vertices, and this shows that this is for the complete graph. So for example, if we write k2 in a graph case, then it's same as this k super bracket 2 sub 2 is there are two vertices and there is one edge, and this is actually, so each one of them is there are k vertices forming a k uniform hypergraph, which is complete, meaning that there is only one edge, and then you write 2 to denote the disjoint union of 2. So this can be rephrased that the max number of edges in an n vertex k graph which has no copy of this hypergraph as a subgraph. So this is a Turan type problem. In undergraduate graph theory, we learned about extremal graph theory and Turan problems, which says that if we have a graph G, and if you forbid a certain subgraph H, then how many edges does G have? If G has the maximum number of edges, then it becomes complete graph. So it must have all possible subgraphs. So it contains H. But if it has no edges, then it definitely doesn't contain H as a subgraph. So there is this is too extreme of the number of edges. So there must be certain threshold that after this threshold number of edges, if you have more than this, more edges than this threshold, then you must have a copy of H. The study about this is Turan problem, and this intersecting hypergraph can be also formulated in this way. So, theorem by Eridich and Corrado. Determines this number. And let's say n is at least 2k, then any n vertex intersecting k graph has at most n-1 choose k-1 edges. So here n being bigger than at least 2k is is a condition that's kind of necessary, because what happens if n is at most 2k-1? Then any set of size k inside of n, any two sets of size k, they intersect. So the question becomes trivial. You consider all possible sets of size k as an edges. So you consider complete graph on n vertices. So n choose k is the answer to this question, these two equivalent question. So to avoid this non-triviality, and we assume n is at least 2k. So let h be on also this number is one of natural guess, because if you consider a hypergraph which has edges, so vertex is numbers between 1 and n, and you consider all the set of size k which contain the first element. Then this is intersecting because any two edges, they share at least one vertex, which is 1. And this has the number of edges in this hypergraph is n-1 choose k-1. So this is natural gas. And this theorem with this example shows that this is exactly the maximum that we were looking for. So let's say H is an intersecting K-graph on the vertex set bracket n. Then we first claim the following. Let's say S is between 1 and n, and let A sub S be S, S plus 1, and so on, S plus K minus 1. So we arrange the n numbers in this way, 1, 2, 3, S, S plus K minus 1. And we consider an interval. So this interval is A sub S. And let's say here we have some other number, m minus 2. And here is m minus 2, 3 plus k. And this is another interval, a sub n minus 2, and so on. So, where m plus I is same with I for positive. Then we consider this interval. Intervals in this cyclic arrangement of numbers. Then, this claim says that at most k of these all possible sets are actually the edges of H. So this is not difficult to show. So this is the ASA, AT. So suppose this AT is in the hypergraph H. Then all sets AS that intersect with AT with TS not in T. S different from T look like this way. This is another interval intersecting with AT. And because S and T are different, there are some parts which are left over. Then you can consider another interval here, which covers exactly the leftover. And we can pair these two up. So when we have this interval, then we consider this leftover part, and then there is one which have exactly that, and then further. And if we have this, then you can consider this. So they can be paired into pairs A T minus I and A T plus K minus I. So AT starts from T, so this is T, and then also this green part is T minus I, then this part is exactly T minus I, T plus K minus I. But what do we know? And this are not intersecting because n is bigger than 2k. If n was smaller than 2k, then one of them is like this and the other one is like this. Each of them has length k, so they might intersect somewhere here. But that doesn't happen because n is at least 2k, so 2k vertices here, k numbers here. 2k is smaller than or equal to n, so there is no intersection here. So this is pair of two disjoint sets. Out of these two, because they are disjoint and because H is intersecting, and at most one of such pair are H's of G, H's of H. This shows that and how many of these are here? So k minus 1 pairs. And one from each pairs are in H. And then AT itself is in H. So at most k of the sets AS are H's of H. So this shows the claim. And now we consider some random experiments. Let sigma be a permutation of this bracket n, which is chosen uniformly at random. And let's say I is an index between 1 and n, is also chosen uniformly at random. And where the choice of sigma n I are independent. So we consider this random procedure, and then we get this random set, which consists of sigma I plus 1, and so on, sigma I plus k minus 1 be the random set obtained from sigma and I. Here, again, we identify n plus I with I. So this, if this is bigger than n, then we consider this as, we consider from 1, 2, 3 again. n plus 1, if this is n plus 1, then we consider 1. So sigma 1. If this is n plus 2, then sigma 2. Then, what do we have? If we consider a permutation, sigma 0, then the claim implies that the probability that A is in the H set of H, conditioning sigma is exactly sigma 0. So we fix sigma and then we choose I at random. Then this has probability at most k over n. Because if we fix sigma, then we put the vertices in cyclic order, and then we choose I. Then this A is chosen from these sets. So sigma is fixed, that means the vertices are put in cyclic way, and Now we choose I at random, meaning that we choose one of these sets at random in uniform way, uniformly at random. But this claim says that there are at most k of the sets are in the H set of H out of n choices. So out of n choices of I, only at most k of them yields the H's. So we get this probability. Then if we don't condition on anything, so this is simply the summation of this probability that sigma is same as sigma 0 times this one, which is at most k over n. And as this sums of all possible permutation, then you get 1. So this is at most k over n. But now we kind of double count the probability in another way. For fixed set A, for fixed set S in of size k, what's the probability that A is in A same as S? You choose permutation at random, and you choose I at random, and you get this. So you can actually compute this, and then you can actually show that this is same as 1 over n choose k. So that all the possible sets are chosen uniformly with the same probability. It's not difficult to actually check that. So A is same as choosing a set of size k in uniform way from all sets of size k, so that what we have that the probability of A is in this H set is same as number of edges in H divided by n choose k. But what we have shown is that this is at most k over n, imply that the number of edges in H is at most n choose k, n over k times n choose k, which is n minus 1 choose k minus 1. So this shows what we want. So what we have done today, we have went through 3 examples of probabilistic method. So there, we use some, some techniques that we construct some probability space, and then we compute the bad probability, and we bound the bad probability so that so that we can show that the random construction that we take, the elements of that our probability space, there are at least one of the elements of the probability space is what we actually have desired. And on the last example, we kind of see how it can be useful. So here we define the random procedure in a slightly different way. Before we just choose, in a natural way, everything in uniform. But here essentially same, but we gave the different interpretation. We essentially just choose one set at random, but which we interpreted in a different way. We choose permutation at random, and we choose one place of starting point at random. This permutation gives this cyclic permutation, and then you choose one starting point. From that, and we add the combinatorial idea, and we combine them so that we have some probability interpretation, explanation about some probability, which provides us some non-trivial explanation. While doing that, we consider some object which is also chosen at random, which depends on the random choice we have made. So this is something called random variable that we will frequently use later. So we choose something at random, and then from that we consider some related object. Anyway, so this, I hope this kind of illustrates what probability method is. And next time we will consider a few more examples of this kind of probabilistic method proof. And that's what we will do next time. Thank you for listening.